All right, so I'm really glad to see so many people here today. I hope this is interesting. This is a new project. It's called, as Ruben was saying, ToroDB. This is a lot of Spanish brand, and this, because it's a project built here in Spain, is probably the first general purpose database ever built by a Spanish organization. So I'm really proud to be here, and I really thank the organization for bringing the interest in this topic and let me speak to you about it. Anytime, feel free to ask any question. I'm here to answer and present this project. It's meant to be a bridge between the NoSQL and the relational world, because most NoSQL projects, most NoSQL databases have to start from scratch in some other way. They have built everything in a new fashion. That's absolutely okay, but we as software scientists, software engineers, we are often told, and I truly believe in that we shouldn't reinvent the wheel, and we should take those pieces that we know that work well and build on top of them. So based on this principle, we thought about creating a NoSQL database, which happens to run on top of a SQL database. We've also been told that SQL databases are slow, painful, difficult, they don't scale, and up to a certain degree that's true, but that doesn't mean that they are bad products. Indeed, they are extremely good for many use cases. With a little bit of tuning and a little bit of probably clever, let's say, algorithms, we can make those be the basic building block of a NoSQL database, of a new NoSQL database. And this is what ToroDB is. So here's what we're going to be presenting. Before starting, a little introduction about myself. I work for a company called 8K Data, where I'm the CEO. This is a company basically related to a software database research and development, and this came out as a prototype project that we've been building and building until it became a final product. We're very specialized in a relational database called PostgreSQL, which I'm sure most of you know, and where we offer consulting, training, and support services. We're also the founders of the PostgreSQL Spain, PostgreSQL España user group, which if you may be interested, feel free to join. Go to postgrespaña.es. And we have become, in less than a year, the third largest Postgres user group in the world, just only after New York and San Francisco. This is something we're really proud of. And of course, I'm available. Here you can see links about myself, Twitter, LinkedIn. Feel free to get in touch anytime, any moment. I'll be happy to talk about ToroDB, Postgres, or whatever, any other topic you may be interested in. So how we came with this idea? We started thinking about NoSQL world, and NoSQL world is a huge thing. We all know this. This is not new. So we looked at the market, and so how big is this NoSQL movement? It's approximately, based on the 551 research group organization research, it's about 14 billion market in the next 5 years, with an annual growth rate of 21% year over year. That's huge. So it's a big market. It's growing. It's still smaller than the relational database market, which is around 30 billion currently. But the pace of growth is clearly outperforming the relational database world, which is the largest software enterprise market in the world. And it's going through all the possible areas where NoSQL can penetrate. It's going to defense, web, biotech, finance, telecom, everything. So it's going everywhere. So this is really something interesting. So we, as a database research company, we're of course looking into this trend and thinking about what it is in the NoSQL world, and if there was some room for improvement, how to improve it. So the first question is why people like or want NoSQL. There's, of course, many possible analyses, but a little bit simple one is there's like 3 main reasons, which are outlined here. The last one is the easiest to explain, so I'm going to start first with that one, because it's cool, right? It's not unknown that many developers are guided by coolness. Hipsters, we all know that. For the good or the bad, I'm not saying it's bad. I'm just saying that most software developers follow a lot of the trends. And NoSQL is a trend because it's cool. Sounds good, and it sounds agile, and all the agile movement and time to market that makes good sound to our bosses' ears. And so it's trending in part because of this. But focusing a little bit more about the technical reasons, the first one is because it's a schema-less. And schema-less fits well, or seems to, with what we call the unstructured data. Nowadays, unstructured data accounts for 90% of the data produced every year, and only structured data for 10%. So we need to process unstructured data, and being schema-less seems a good fit. So NoSQL databases are popular in part, this is of course our analysis, due to the schema-less feature. And also because of the high availability. There were some talk before about the CAP theorem here. We're going to talk a little bit about that later on here also. But basically, high availability is a must nowadays. It's one of the key components of what is called big data. We're here for big data. So we need to be highly available. And NoSQL databases, which happen to scale well across many nodes and retain some degree of availability, are also cool, are also growing and are wanted because of this. However, we're going to show here that this may not be exactly the case, or the reality is not as nice as we may think. Let's talk about first about this schema-less. I'm sorry to say, and you're free to disagree, that it's almost a fallacy. There is no schema-less. Let's look at this document, for example. There's also a fallacy in the document. I'm not that tall. But other than that, if we think about this document, right, it's a schema-less, right? Because, height can be removed, or the surname, or hobbies, or, I don't know, can vary. But variation doesn't mean that there's no schema. Indeed, this is the schema. When it's pointed out in blue, it's a schema. It's talking about naming a field. And that's not a column on a table, definitely not, but it's a schema. It's meta information. That's what is a schema. So there's a schema in there. Also, the open bracket, that means an array or a container, if you prefer. That's also a schema. It's one character schema, but it's a schema. It's telling that a list of elements is following behind. But if we look even deeper, like for example, on a BSON representation, the storage format for mongoDB, the BSON format contains even more metadata. For every field, there's a strongly typed information. So the name in BSON is encoded as a string, and there's a byte character indicating that the following attribute is a string. So there's name definition and called the key, and there's the type, strongly typed data. That's what I call metadata or schema. But it's even worse. I mean, if we look at the container, like hobbies, which was a container, an open bracket, an array, if you want to call it that way, when you look how it's represented internally in BSON, it is really an object, where the keys are numbers. So we have the key 0, which is in a string, and the key 1, which is also another string. So both are, again, as I was saying, metadata, and in turns, this means that this all is not a schema-less. There is a schema. So the first trend about NoSQL is, the first thing that people like about NoSQL is that it's schema-less. And we are saying here that it is not schema-less. It varies from document to document, but there is a schema. So we don't want to call it schema-less. We call attached to schema. The schema is attached to the document, but it's there. There is a schema. And this carries an overhead. Because we need to store, think about this, collection of documents where all of them are similar, let's say even equal, if you want to think it that way. All of them, every single copy of the schema of the collection is going to have the same schema attached to every single document. This has a cost that is not 0. And we're going to show how in ToroDB we take advantage of this. The second fact that I'd like to discuss, but a little bit less detail because it's very well known, this stuff, is the high availability. Sure, there is some ways of doing highly available systems, distributed systems, but we know it's hard. The CAP theorem, which was already discussed here some minutes ago, explains us how hard it is. And true is that most systems that advertise themselves as completely available are sometimes, but definitely not without restrictions. If you think about mongoDB, for example, there are some numbers that I don't know if you're aware of, but basically you can incur in high data loss unless you really take a lot of care about what you're doing. And definitely this is not the default. I don't know if you know this guy, Jepsen, or Afir, or whatever, because he changes his name every single day in Twitter. So I don't know how to call him. This guy's a little bit crazy, but he's a genius. And he has built a software called Jepsen, which creates artificially network partitions and basically allows a distributed system to fail under several scenarios and to test how resilient it's to failures in network partitions. Using this software, Jepsen, in a blog post, which I recommend you to read if you haven't, which is at the bottom of the slide, basically proves that mongoDB system can lose up to 42% of the data under an acknowledged mode, which is, yeah, well, you know, it was a default until 2.2 is no longer the default, but still a lot of people use it. Say, it doesn't matter if I lose a little bit of this log data I'm pushing to the mongoDB system. Well, it might not be a little bit. It might be a 42%. But even if you run on safe mode, which is the default, you can lose up to 37% of the data, which is, again, definitely not a tiny fraction of your data. It's only under the majority it is safe. Now, my question is, how many benchmarks that you have seen about mongoDB are running in majority safe mode? So there are definitely some trade-offs about high availability. And there's more NoSQL struggle. Like, durability is not sometimes even guaranteed on a single node. And I'm not going to mention examples, but it's not hard to find those. There are many NoSQL databases that even on single node, they are not completely 100% durable. There may be a window of data loss. OK, I want to give an example, but not to put any blame, just because it's easy. Everybody knows it. mongoDB, for example. It's safe on a cluster, but definitely on a single node, there is a small window of possible data loss. So if you want to have a really durable system, it might not be your better choice. And finally, and going back to the CAP theorem, well, definitely this systems trade consistency for availability, and that's, of course, the easy path and makes sense. But programming for an AP system, one that is not consistent, like one that is eventually consistent, or it's not linearizable, it's really hard. It puts a lot of burden on the programmers, on the application layer. And this is sometimes, most of the time, I would say, overlooked. We just take it, but then you may want transactions on top of it, or you may want some linearizability properties, which you may not have. And this is really difficult. So it's really a gift if you, at some point, could have some transactions. And all of these consequences come from the fact that most NoSQL databases built everything from scratch. They, they took everything from a clean piece of paper, and that's, of course, good, but didn't take advantage of anything that already existed. And some things like journaling or concurrency are really hard. Again, referring to the same example, no pun intended, really, journaling was added like as an afterthought not so long ago. Concurrency is not even there in a practical sense. And that's why it's really hard. It's really, really hard to do it from scratch. So we asked ourselves the question, can we do a better NoSQL? And, well, first of all, we need to we thought about departing from the document model, which is really appealing, and a lot of people like it. And I think that's one of the best advantages and the best innovations that NoSQL brought, the document model. But we, software engineers, thought about the don't repeat yourself principle. Like, why not take something that already works as a building block? Like, for example, relational databases. They are proven, they are durable, they are highly concurrent, and they are flexible. Not all of them, but most of them. They're flexible enough. And so why not base it on a relational database like Postgres? So this is what we thought. And going back to the schema-attached problem that I was talking about before, if you look at the collection, a large collection, well, this is not a large collection, but it serves as an example. You see that there are some documents that repeat the same schema, the same structure. In red, for example, you can see that there are two documents which have a field A and a field C. Both are numbers or integers. So they have the same schema. So it repeats a lot. So we thought, what about factoring this out? And say, OK, this set of documents have this schema. This set of documents have this other schema. At some point, we were asked the question, like, how many different schemas you may have on a huge collection, maybe a large number. We did some tests, and the reality was that it's not. Even in large collections with millions and millions of documents in the normal use cases, there are at most thousands of different schemas, of effectively different schemas. So this is a high price you're paying because you're repeating them all the time. There is, of course, some degraded cases, but in most data sets, you won't find more than 1,000 different schemas. If you think about it, this is really how documents are stored on a schema-less database. If you think of documents of different schemas for different colors of pieces of Lego or whatever, they're just all thrown in the bag, no order. Now think about what is for the database to search. Why most people in NoSQL databases are extremely concerned about indexing. Because without indexing, you have to scan for the whole thing. You need to read the whole database to find your green or purple piece, which is what you're looking for. So this is the overhead you're paying. We had some inspiration. There was a presentation by a Postgres specialist called Christophe Petus, which basically showed this slide in a presentation, and you see that if you compare the relational and the mongoDB storage required for storing the same data, there is a huge difference, like an order of magnitude. If you take the data, create the schema manually, and store it in relational tables, you require less than 1/10, approximately, of the disk space. Well, of course, you're not going to create tables manually for every document, but what about creating them automatically? Software can do that. And what about creating a large number of tables? Well, I said before that the number of different schemas is not large. But we also did an internal project the year before called BTP, Billion Tables Project, where we created the database on Postgres with a billion, American billion, 1,000 million tables inside it. It worked quite well. And we demonstrated to ourselves that creating a large number of tables is not a problem. So, with all this, we built ToroDB, which is the database, the open source database that we are presenting today. So what is ToroDB? ToroDB is an open source, it's document-oriented, based on JSON database that runs on top of PostgreSQL. However, JSON documents are not stored inside the database as a blob. They are stored relational. They are split, and they are stored in relational tables. This is quite new, quite unique. This leads to really significant I/O savings and performance improvement, because we're factoring all the schema repetition that I saw you before. And on top of it, we have added wire protocol compatibility with the mongoDB protocol. So basically, you can use your Mongo tools, Mongo client, whatever, to connect to this database, to ToroDB, and your data will be stored in a Postgres database. What are the benefits of doing so? Well, first of all, we got a 100% durable database. You know, Postgres if anything, it's known for its reliability and durability. So here you have it. You want something extremely durable, here you have it. There is also a highly concurrent system, because Postgres it is. It is a highly concurrent system, so you get a highly concurrent system with great performance. And it's compatible with the mongoDB API, so you can use the same tools, the same platforms, the same applications. And it's currently implemented the full set of, the query or select, if you want to prefer it, call it that way, API functions. As I was saying, data is not stored as a blob or as a binary column. It's stored in tables. How do we do this? So we take a JSON document and we basically split it by levels. Think of hierarchy levels, and each level is going to a different table. That's quite simple in that. And then documents are classified by type. We mean by type the attached schema. So, the set of the ordered set, basically, of key values and their types, that's what we call a type. And documents are classified by type. Then there is a structure table, which is basically what contains the structure, the schema of those set of documents that have the same schema. Keys of the documents, keys of those levels are mapped directly one-to-one to columns in the tables. So, it's very easy to spot which value belongs to which attribute. And of course, we need to create tables dynamically, and this is not a big deal. So the software basically analyzes a given JSON document, it splits it into levels, find the type that defines that document, in other words, the set of keys and the types of their values, and tries to find a table that matches exactly that structure. If there is a table, it stores the document there, and of course, throws some pointers to locate the data. If it doesn't, it just creates a new table. So this is how ToroDB basically stores the information. If you think how any NoSQL database stores the information, it's something like this. All the types are mixed and put on the same bag. We analyze the types, classify them, and store them individually in a way that looks more easy, because documents are classified by type. Let's show this more graphically in an example. So imagine a document like this one, where you have a field name, field data, which is a nested object, another nested object, which contains another fields. So first of all, I mentioned that this document is split into levels. So here we have basically 3 levels. The level which contains name, data, and nested, the level inside data, and, 4 levels. The level inside nested, and the level inside deeper. So we first take this document and split it into 4 levels, which are these ones. So I was saying name, data, which is a nested object, we represent by an empty object, and nested, which is again an empty object. Then we have A and B, which was inside data, so that's the second level. And then J and deeper, which is the nested level under the nested attribute. And finally, A21, B hello, which is the other nested object. So first of all, split the document into these 4 parts, and then store them in tables. As tables are created dynamically, they have row names. They're not related with anything. And this is this is true data capture from ToroDB, where you can see that basically this is the information here. The underscore ID in the table T3 is the mongo underscore ID field automatically generated. So here we have all the data represented. Here you can see that these 2 documents, the second and the 4th one in this example, have exactly the same type. They have one field called A, which is a number, and a field called B, which is a string. They have the same type, so they are mapped to the same schema. So we store them on the same table. We are not repeating the schema. So in this case, you can see that those documents went to the table T1, T_1. And of course, to glue this all together, we have a table which is called structures, which contains all the structures. The structures are the schema, the data types. So here you can see that the root level it's a T2, which means data is going to be on table number 2. Then data is going to be on table number 1. And nested has their root object level on table number 3. But then, if you go on deeper, you'll see that there's a table number 1 pointed out, because it was on the same table as the data. And remember the document with field A and field B. So they are on the same table. With just this information, we can glue the document back all together. And then there's a table which relationally maps documents to structures. In this case, document with ID 0 is mapped to structure 0. Of course, structures, the table structures, have a way lower cardinality than the documents or the root tables, because many types are shared by the same documents, but different documents, sorry. What are the advantages of doing this? First of all, we have a great storage saving. We're not repeating the attached meta information, and I explained before that this is a huge penalty. So once we factor that out, we have tried with several data sets. Of course, this varies, and your mileage may vary, but we have found that storing the same data under ToroDB or mongoDB for comparison requires from 29% to 68% the disk storage required by Mongo. In other words, up to more than 3-4 times less, which is quite a huge achievement. Think about you're having a multi-terabyte database, you're paying a lot of money to store all that extra meta information that you're repeating. Or for the same price, you can get a faster storage. Or maybe your data set now fits in memory, and your performance basically gains 1 or 2-fold orders of magnitude. So this is really something that we're really surprised and happy about. There's also really good performance. Despite that we are basically doing an analysis of the document, splitting into parts, maybe creating tables dynamically and storing it, we have a highly concurrent system. And despite that single insertion document may not be as fast as all the systems like mongoDB, the truth is that concurrent operations are extremely fast. We're able to basically utilize the whole number of CPU cores of the database, and everything's running concurrently. There's no locking, so we're really fast in terms of insertion. So for example, looking at document insertions in batch of 5, we get this performance where basically we outperform mongoDB on this test. And if we have a batch of 1, it's even faster because we're throwing more concurrent operations at the same time. So we're achieving greater storage savings, greater performance. And there are some types of queries, may not be the most useful case, but they're quite interesting, which is what we call query by structure, or negative queries. Think about a query which is asking for a field that doesn't exist on the database. Well, in regular schema-less databases, you don't know whether that field exists or not, unless it's indexed. But of course, if it doesn't exist, it's probably not indexed. So you have to scan the whole database to find that that document doesn't exist. So it's really painful operation. However, on our case, on ToroDB, querying by a field that does not exist is extremely cheap, because we only need to look at the structure. This is a table called structures, because fields are represented on the schema. So we can find, just looking at the schema, whether that field exists or not. And indeed, this schema, this number of structures is so small that we are caching it in memory. So in other words, this type of queries, we're answering them from memory. So we're infinitely faster. That's a division by almost 0. So last month, just a couple of weeks ago, we launched ToroDB in developer preview version. So it's a work in progress. And we basically support right now the CRUD operations and most of the select API. It implements the Mongo protocol, as I said, so you can use the Mongo tools like in the Mongo console. Not everything is implemented yet, but this is open source. We are following release early, release often policy, so you're really welcome to join the project, to test it out, send back reports, give us feedback, contribute code. We really want to make this open source available to the public as soon as possible. That's why we publish it, as I was saying, a couple of weeks ago. And license is open source. It's AGPL version 3, so it's a widely known license. And as I was saying, you can go to github.com/ToroDB. You can find the source code, all the source code there. How to use the software? You can either clone the repository and build with Maven. It's very simple. There are some already prepared jar files if you don't want to mess up with compiling. You can get them directly from the link. There's the link on the web page too. And then just use this is developed with Java. So just basically java/jar and the name of the jar file, and some options, which basically are the host database you're connecting to the user, and the port where you want the system to listen on, which is usually the mongoDB port, to remain compatible with most tools. There's been a huge community response to our initial launch. After a couple of days of launching this project, it got to Hacker News and was a really big hit there. There was a really huge amount of Twitter stream. There were a lot of blog posts talking about ToroDB, and honestly, I'm so happy about it. I'm really glad about that. If you look at the GitHub repository, in almost one day, we got like 500 starings of the repository, which is something like quite unique. We became #2 trending repo that day on GitHub, just only following a Facebook project on databases that they released the same day. But that was already quite huge for us. The opinions of people are quite interesting. This is quite good feedback for us. There was people saying things like, it speaks natively the mongoDB protocol and saves your data, or best of both worlds, or that basically more proof that everyone wants mongoDB data interface layer with better way of laying bits on disk, which is basically what we do. Or it's like Mongo, but it's not built on a platform of fail. This is not my opinion. This is all those people's opinion. Or the best of MongoDB with the best of the true databases, translated from Spanish. So there's been an overwhelming community response, and I'd like that trend to continue. That's why I'd like to invite you all to give it a try, to report feedback, to report patches, test use cases. It's still developer preview. We wanted to release as early as possible, so there's definitely a lot of stuff to do yet. But as I was saying, the response has been great. The community has been giving us a lot of feedback. There's already some contributions, and I'd like to invite you to join this project as much as you can, as much as you will. What about the roadmap? We're planning a full 1.0 release on Q1 next year, probably at the end of Q1, which basically it's going to include full support for all the Mongo stuff, including replication protocol. As I was saying at the beginning, we are a research and development company, so we are thinking about how to implement the replication protocol. We also want to improve on that, if possible. So we are looking right now about a Paxos implementation of the replication protocol, which may still be compatible from the outside, but internally it will work better. And we expect this version to be production ready. There are some people already using it for kind of production systems, but it will be full production ready by then. And of course, really high compatibility with the MongoDB API. And finally, this is a peek on the future of what we are going to do for ToroDB, and especially for a conference like this one, talking about big data. We believe that there are some NoSQL databases which struggle when they're talking about big data, really big data. They can do it, but they're definitely not highly tuned for that. But it's a shame because the other options for doing this big data are way more cumbersome. They're not as easy as a regular NoSQL database. So we want to make it available for the big data community, some product which is easy to use but also good for this kind of workloads. So if a NoSQL database stores information like this, all documents are thrown and classified, all mixed together in the same bag. And ToroDB, as long as it analyzes the document types, classifies them into tables, and stores them like this. Different tables with this, for each different document type, and all the same document type inside the same table. We thought about, what about using columnar storage, which is something that can be done in Postgres with a project called CStore by a company called Citus Data. And in this case, we would store data in columns, as the name implies. So fields of the same type will be on the same column. This is, of course, great for doing like aggregate operations, and it works really well. And you can perform some operations like this type of operations, aggregate operations, extremely fast. If you compare this to all the NoSQL or schema-less databases, you'll find that, for example, computing the average salary on a collection of documents which represent the staff of a company, it's really hard because the salary field may not be there on every document. You have to scan the whole documents and find that salary field and then compute the average. You will end up scanning the whole database. Here in Toro, we first split documents by type, so the salary will be only on a single table. And then this table start in columnar fashion, which means that all the salaries are put together and compressed. So the speed performance is extremely different from storing everything as a mixed bag. And we did some initial benchmarks. This is not going to be even in 1.0. This is experimental stuff. But we tried to see what is the storage difference between storing things in Toro, in mongoDB, and vertical Toro, which is the name we chose for this big data variation of ToroDB, which is going to be an option. And basically, you can see that some benchmarks, some data sets were reduced down to 20% of the storage that Mongo requires for storing something. And we even got some benchmark, honestly, a little bit artificial, not made by us, but it's still a benchmark, which reduced the data storage to 1.17% of what Mongo requires, from 4,500 megabytes to 50. You can imagine the performance differences of this. So this is basically it. We're really grateful of many software projects with which ToroDB would have never been capable of bringing to life. As I was saying, don't repeat yourself. We have built ourselves and many different projects which basically give us a lot of power. And these projects are PostgreSQL, of course, the Netty framework, which we use for all the asynchronous operations with high performance, Juke as a great framework for performing the queries to the database, and of course all the usual Java stuff, Java, Juice, Findbags, and the Hickory connection puller, which is awesome. So this is basically it. I'm now open to any questions that you may ask. Thank you.